So this is problem 10. It's a little different, but not too much different. Ball hits a wall and as a result changes its velocity and momentum. Force of collision is given, so let's restate this here. Force of collision given as minus 10,000 t minus 0.01, and then you square this plus 1. All right, collision itself takes time interval delta t is 0.02 seconds. Calculate impulse delivered was always the change of momentum. So we're looking for J. Unknown is J. And then if you go back and look at your options, that is J is the final momentum, the initial momentum by definition. J is the antiderivative of force during the collision, dt. And then J is the area under the graph. So looking at the options that we have here, it's pretty clear, I think, that this is not going to do the trick. Neither will this, but the middle will. So we have we have to take the antiderivative of this function, 10,000 f t 0.01 squared plus e of resulting here. That now this whole collision took place during a certain specific time, and that time interval is 0.02 seconds. So what I can do is I can integrate from 0 to 0.0 seconds. Just call the beginning to be 0 and then the end, beginning to be the beginning of the change and then the end to be the end of the change. So I'm going from 0 to 0.02 of a second. And whatever I get out of the integration is going to be the actual impulse delivered. So I might as well do it. False. So we'll get here minus 10,000. This is going to be 10,000 over 3. Then time 0.01 cubed plus t. And about integration of 0 to 0.02. Make sure that this is actually right. So we take the derivative with, yeah, I think that's correct. So then J, the magnitude of J is what we're going to end up here with, but J equals probably actually, well anyways, so J equals, and then run this thing through. We have to plug in the numbers, so let me do that and I'll get back to you with the answer. I got 0.013 Newton seconds. So that's problem 10. And then should do problems. Well, actually, I'm going to solve problem 12 first. So similar but different. Hits a wall, result changes massive momentum, average force, collision is such, collision self takes such impulse. Okay. So the average force of collision AVR is 2000 newtons, and then the time during which the collision takes place is 2 milliseconds. So we're looking at 2 times 10 to the minus third of a second. And calculate the impulse. So what I'm looking for is J. J is the unknown. And again, J, couple options here, is final momentum. J could be the antiderivative f dt, where this is the net force during the collision. Then, well, it's supposed to be, but, and then J amounts to the area. If the area is positive, then J is positive. If the area is negative, excuse me. So I'll leave it like that because I'm not sure how you would label area here as a vector. But so anyway, the however, this also can be the average times the time. Now looking at this, it's pretty clear that this one's not going to give you the answer. This one will not give you the answer, but the middle one will. The middle one will. And so going off of this one, let's calculate J here, the magnitude of J as, I suppose we could say not just the magnitude, but we could say this is just constant last 1,000. And in that sense, force points to the right. It's positive 1,000 newtons. So one-dimensional case. And what we have here is force, the average force, times the time. And in that case, this becomes almost trivial because what we have here is 1,000 times 2 times 3rd, and that gives you, well, this is over 1,000, 1,000 like 4 seconds. Force positive. So positive 4 Newton seconds, and I could keep the vector note, assuming that assuming this is actually a one-dimensional problem, and the plus indicates that the force points to the right. All right, so that's 12, and now I think I can ask you to solve problems off of the worksheet. So let's see which ones. All right, so do problems 9 through 13. You should pause the video and then problems 9 through 13. And now I'm going to move graphing problems, types that I need to see. But let's move up. All right, so here's the first problem from well, I think it's still the same worksheet, but there are graphs there that you have. So the 10-gram ball, put that here, 10 grams, 0.0 1 of a kilogram. Is thrown straight at a wall, strikes it at 4 meters per second. So let's draw a picture here. So what I have is a wall, and here's this thing, and it moves at 4. The initial one is 4 meters per second. The velocity graph below depicts the force during the collision. Note that the force during the collision is positive. So I'm going to put here force during the collision is positive. That implies that what I just drew here is actually wrong. All right. You might not see why yet, but let's get rid of this picture. And like this, and I'm going to start it again. So if the force is positive, then the wall has to be second. Here's the object, and the object is moving left at of -4. And the reason why I know that it has to be -4 meters per second is because the force is positive, and the force is positive because I see it in a graph. So when this object collides with the wall, the object ball colliding with the wall, during the collision, the force points in which direction? In a positive direction. The positive because the graph shows me that the force is positive during this time interval. And if the force is positive, then the object must be from the right, moving towards the left. That also means that after the collision, object when it's right, its velocity must be positive. It's just that I don't think I know what it is, or do I? Graph below depicts the force during collision. Estimate the speed with which the ball bounces back. Okay. So I'm looking for the positive. I'm looking for the final velocity of the thing. So what I can do here is I can go off of well, there's a change of momentum, so I can start there. I can write that change of momentum, delta P, is J. Now the change of momentum, that's just final minus initial, is J. So let's substitute and see how far I go with this. Final momentum, which mass the F, that's good because I'm looking at the F and I have minus initial momentum times mass I have VI equals J. So let's plug in the numbers. What I have is 0.01 times F minus station here minus 0.01 times VI, which is minus 4. So times minus 4 equals J. Now I could calculate for the final velocity here if I could figure out J, but I can't figure out J because I have the graph, right? J, I have a couple options. So J by definition, but I already used these equations. That's going to give me no progress. J is also the well, the integral, which amounts to being the same as so anyways, this isn't gonna do it. This here amounts to be this, as J is the area under the graph of the force. Now I don't really know what the equation for the force is. That's not given to me. I'm gonna be helpful, but this is going to be helpful because what I can do So I can look at the graph and I can approximate the area here, right? Let me use a different color. So yeah, triangle will do the trick, right? So what I can do is I can draw, here's my triangle. The area under this triangle is going to be, roughly speaking, the area that I have under the graph of the force. It's not going to be exactly the same, but it'll be good enough for my purposes. And so what I can do is I can just write here that, oh, I see, I have to change this. I can just write here that area, roughly speaking, 1/2 times base times the height, because I'm looking at a triangle. Now base here is 4 seconds times 4, and the height here is 32.5. 32.5, in other words, area equals 2 times 32.5, so we have 65. And units would be Newton seconds. I'm multiplying force times time, so what I have here. So this would be 65 Newton seconds. And note that, roughly speaking, approximate. And so what I can do is I can write here 0.01 times VF minus 0.01 times minus 4 equals 65. And then I can just finish this off. So this would be final. I guess this becomes plus 4. And then pull this in. I have a 500. Let me get it. I'm not giving you. Yeah, about right. So what I get here, final velocity. That's just, no. There's something iffy. Like, definitely something iffy, because if you look at it, I mean, we're going to get a huge final velocity. If anything, that velocity should be this final speed should be smaller than the initial speed. Let me roam around and see if I can find an error here. And I found it. And the area, the place where the error is right here. This is milliseconds. Put this here. That's milliseconds. Right. What that really means is that what I have is not 65, but how did we do this? 65 times. So let's fix the issue here. 65 Newton milliseconds, if anything. So we should have here 65 times 10 to the minus third newtons. This should be. We should also fix this issue. This becomes times 30 newton seconds. That means that here I have to have third, which means that this becomes 6.5. And now we're looking at something reasonable. So 6.5 minus 4 gives us 2.5 meters per second. Note that this is plus, and plus is good, because we know that the final velocity here must be in a positive direction. Okay, so pay attention to the units, and you can approximate the area if you have to. All right, so that's one graphing problem. I'm going to solve one more, and then yours is this whole worksheet finished. So let me bring another problem from the worksheet. And so here's problem 4, and in this specific case, the mass is 0.2 of a kilogram. Initial velocity is 7 meters per second. Actually, at speed, velocity is going to be negative. See, again, force here is positive. So I'm going to, from the picture here, I see that F is positive. And that implies that if I want to draw a picture for this, the force, this is where I have to have bounces off a wall. So here's the wall. Force has to be positive. That means that the object must be coming in towards the left. The initial velocity is minus 7 meters per second. When the object collides with the wall, because the wall is on the left hand side, the force itself can now point in a positive direction. So here's force F, which is positive, and then the object bounces back and it moves with a final velocity in positive direction. So here's the final velocity. Am I looking for the final velocity? No, I think I know the final velocity. Bounces back at 6 meters per second. So it's 6 meters per second in this case. Okay. So I have, and this is plus. And the signs matter. So negative 7 meters per second, so that's the initial velocity. Final velocity is positive 6 meters per second. And then I have the graph, I have the mass. The question is, what is the maximum force? And what is the average force during the collision? All right, so, well, the graph is just a triangle, by the way. Note that that's approximated, the graph of the force is approximated with a triangle. And so let's see where we get, I can easily calculate the change of momentum, right? Because change of momentum is final minus initial. I have everything that I need for this. So let's calculate that. Final momentum minus the initial momentum. That means mdf mdi. And so this gives me 0.2. And then final velocity is 6 times 6 minus 0.2 times the initial velocity, which is minus 7. And that negative is important. This is where I will often test with this. So what I get here is that the change of momentum equals, let's see what we get, 1.2 plus 4. That gives us 2.6, positive 0.6, and this would be kilograms times meters per seconds. And now that's of course also J, right? Because by definition, J is change of momentum. So I have that. And then I have a couple options here. I can use J equals the area. And I could also use J approximately average force AVR times the time during the collision. And it so happens that one of the unknowns is the average force during the collision. So I can use this equation here. Let's go ahead and use so F average. Let's do this first. F average. It's going to be J approximately force average times the time. So J is 2.6, positive 2.6, and that equals F average times the time during which the collision took place. So the time interval of the collision is just, it's going to be from, I'm looking at the graph, time interval is delta t is 0.1 of a second. All I have to do is divide this by 0.1 seconds, that's 1/10, so this gives me 26 newtons average force during the collision. So that part is done. Now for the maximum, so F max, solve for F max here. I have already used this one, right? Already used this option, so I can't reuse it. I'm gonna go after this. I'm gonna write here J is the area. J equals area, but it's the area of the triangle, so half times the base. The base is just delta t, the base of the triangle, and then the height of the triangle. The height of the triangle is maximum force. Right? If you look at the triangle here, the base of the triangle is just delta t, and then the height of the triangle, the height of the triangle is just maximum force. So that's just F max. So let's go back here, plug in what we need to plug in. So it's 2.6 equals 1/2 times the time, which was 0.1, and times F max, what I'm after. That gives me 26 times 2, which is 52 newtons. That would be the max force, so the max force is 50. Okay. So now yours is to finish, do all the problems on the worksheet, but you have done some by now. presume. So really what you're trying to do is to finish the worksheet, and that will become your homework. Submit it to Canvas, and that will do for the introduction to this unit.